Hi, folks. I just wanted to finish up this little bit about continuity. Okay, so this is where we ended today's class, where we had thrown this graph on Desmos, see what it got us, and then we saw how the infinite discontinuity was pretty obvious, but that removable discontinuity, we really kind of had to hunt for that. And so the question I left you with at the end of class was, how can we use algebra to determine the location and types of the two discontinuities? And so someone had said factor, and that's exactly what we're going to do right now. Okay, so I'm going to take the function, and we have x squared minus 3x minus 10 in the numerator. And in the denominator, we have x squared plus 2x. And when we factor that, the numerator will give us x minus 5 times x plus 2, while the denominator will give us x times x plus 2. And so that common factor, x plus 2 and x plus 2, that's what we wrote earlier in the limits day 1 notes, that indicates that there is a hole at x equals -2, okay? And so that's something that we learned at some point in the past, but now we're connecting it to what we're doing now in calculus, okay? So that common factor gives us that hole, or that removable discontinuity at x equals 2. And let's see how we would find out about that infinite discontinuity. Well, check out this factor. If we set x equal to 0, that is a factor that is only in the denominator. That means that we have a vertical asymptote, and I'll abbreviate this as VA, but there's a vertical asymptote at x equals 0. So if you have a factor that's in the top and the bottom, that's going to be a removable discontinuity. But if you have a factor that is only on the bottom, that's going to be an infinite discontinuity, okay? All right, so let's take a look at one more part to this. And that is, are either of the discontinuities fixable, okay? And if so, fix the discontinuity. And so what I mean by that is, can you, or can we, patch the function so that it is continuous, okay? And so let's bring our picture down here. All right, so I'm gonna cheat. I'm going to copy this. Whoops. And we'll shrink it a little bit to fit. All right, so here's our picture. Now, if we think about this literally as patches, okay, I can put a patch right over the hole in the function, right? I can put a patch there, and then that part of the function will be continuous. And so the way we do that is we have to define the y value that we would put there. And we're going to do that using the factoring that we had above, okay? And so if I go up and I grab that factored version, okay, and let's copy that. And let's bring it down here, okay? So this was our factored version. And once we factored and we reduce the factors that are common between the top and bottom, and then we want to plug in -2. So -2 minus 5 over -2. That gives us -7 over -2, or 7/2. And so if we say that at x equals -2, we plug in a point at y equals 7/2, then we will have fixed that discontinuity. Okay. Now, the infinite discontinuity, however, is not fixable. I cannot take part of the graph that's going up to positive infinity and somehow connect it to the bottom of the graph that's going to negative infinity, okay? So we can only patch the removable one, or we can only fix the removable one, but we cannot fix the infinite one. And the way that we're gonna write our patched function is like this. We're going to say f of x equals, and we're going to write two different functions. One is the original, x squared minus 3x minus 10 over x squared plus 2x. And for that function, that is where as long as x is not equal to -2, all right? So x is less than -2, x is greater than -2. But then we're gonna say that when x equals -2, we're gonna give it a value of 7/2. And that will be the same as saying, let's put a pink dot where that hole is, and now we've fixed the removable discontinuity. All right, one more example before we summarize continuity. So for example 4, we have another piecewise function. And I'm going to do this in 3 different colors because we have 3 different pieces here. And I want us to understand how to read this and draw this and answer the question. Okay. So this says if k of x looks like this, okay, meaning that when x is less than 2, we're going to say it is defined by 3x minus 2. The next piece of the function is at x equals 2, the y value is 5. And finally, at x is bigger than 2, we're going to have the function as x squared. Okay? All right, so let's see what's happening. All right, now if you are a visual person, it might help to draw a little picture just to see what this graph looks like. Okay. Now I'm going to mark x equals 2 here because that seems to be an important juncture on our graph. But to the left of that pink part, it's going to look like 3x minus 2. And that we should know is a linear function, okay? So we know that this is some sort of line. And what does it look like when x is bigger than 2? Well, it should look like some part of a parabola, okay? So we're saying that part of this graph looks like a line and the other part looks like a parabola. And so if we plotted this, we might see that we would get a picture kind of like this for our line. But because this is only less than, I'm going to make this an open circle when I get to 2, okay? Now, how do I know how high to draw that point? Like, what's the y value there? Well, let's see what happens. If I plug in 2 here, I'll get 3 times 2 minus 2, which is 6 minus 2, which is 4. And so this has a y value that gets close to 4, okay? Now, the green one is pretty easy. That's a point. So at x equals 2, I want to draw a point at 5. Okay. Now the last part, that light purple part, is x squared. And so x squared, but we don't want to just draw a parabola. We want to make sure we know where to start. So let's plug in 2. and see where that goes. 2 squared will equal 4. So it looks like the parabola also starts here, okay? Again, it's not a closed circle there because this is greater than, and then it's going to be the parabola, okay? So we've got a line to the left of 2. We have a point at 2, and we have a parabola to the right of 2. Okay, so that's what it looks like visually. Now, if we look at it visually, is this function continuous at x equals 2? And I think we would all look at this and be like, there's no way that function is continuous at 2 because you had to pick up your stylus to draw different sections of it, right? And so we can look at this and say that it's not continuous. But the challenge here is to say, well, we need to use the definitions of continuity and limits to determine whether or not k is continuous. So let's use some of the language we've learned. We can say that k of x is not continuous at x equals 2 because, and let's use our checklist, okay? The limit as x approaches 2 of the function. So what about when we get to x equals 2, what y value does it get to from both sides? Well, it gets close to 4, right? When we plug 2 into the left curve, or the pink curve we got 2, or 4, when we plug 2 into the purple curve, we also got 4. So what that means is the limit from both sides is 4. Well, what else is on our checklist? We need to find out what f, oh no, sorry, not f, we're using the function k of 2. Like, what is the value of the function exactly at 2? And to answer that one, I have to use the green part of the piecewise function, okay? So k of 2 is 5. Now we can say, since the limit, oh no, sorry, we said because those two things. Okay, now since the limit as x approaches 2 of k of x does not equal k of 2, there is a discontinuity at x equals 2. Okay? So I know it's a lot of writing, but especially for those of you who are newer to this class, this is my expectation that we are able to not just compute numbers, but that we can understand the concepts and be able to explain those concepts, okay? Now I'll finish up this video just by taking a look at this summary piece right here, okay? So we've talked about the removable discontinuity, we've talked about the jump discontinuity, and we've talked about the infinite discontinuity. And so all I've done is put into a table here some things you might look for in terms of limits. Okay, so you can use this as a little bit of a checklist for yourself on how to decide what kind of discontinuity you have in a function. Okay, so I hope you take the time to watch this video. When we come back on Monday, we'll start here with limits involving trigonometric functions. Okay, all right, folks, take care, and I will see you on Monday.